بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. This is part 2 of rating and designing of compact heat exchangers. We have said that in order to calculate the pressure drop, which is very important for designing compact heat exchanger or any heat exchanger for that matter, you can use this equation. This equation has two parts or two terms. This is friction and this is acceleration, deceleration. You can add to this other sources of pressure drop if you want to. We have seen that using the definition of the hydraulic diameter as force multiplied by the 4 multiplied by the minimum area divided by the perimeter, you can get this relation between heat transfer area and the hydraulic diameter. So the heat transfer area divided by the minimum flow area equals 4L divided by dH. So you can actually take 4 times L multiplied by dH and substitute with A over AF. This is what has been done for these two equations, from the above equation to the second equation. Of course, in order to get to this equation, you use the definition of the hydraulic diameter as 4 multiplied by the minimum flow area divided by P. You multiply L by L and then you can get actually the relations that heat transfer area divided by the minimum flow area equals 4L على DH. Of course the heat transfer area equals P times L, and this diagram shows some kind of a flow inside some kind of conduit or a pipe. The length of the flow is L, the perimeter is P, and the heat transfer area is A, which is equal to P times L. So this perimeter times this perimeter for this arrangement times this length will give you the internal heat transfer area. That's why actually when we multiply P times L we get the heat transfer area A. Now we are going to move to plate fin compact heat exchanger. Of course here we are talking about gas to gas compact heat exchanger, and this sketch show very important parameters for heat exchange between cold fluid. Let's say this is side 1 and this is side 2, and the first fluid is going to enter in this area for this plate spacing, and this one is going to enter in this spacing between the plates. The volume of the heat exchanger is going to be multiplications of Ln times Lc times Lh, and the frontal area actually it can be written as we're going to see later. The frontal area for side 1 is Ln times Lh, and the frontal area for side 2 is Lc times Ln. These are some types of fins that are used in gas to gas compact heat exchangers. Rectangular fin, offset strip, triangular, perforated, wavy, and louvered. So any one of these fins can actually be any one of these types. This is again shows the two fluids entering gas to gas compact heat exchanger with different geometrical parameters. For example, this side, now the side 1, we call it the cold fluid, side number 1, and this is side number 2. And now you can actually find the frontal area for gas number 1, which is L1 times L2, and the frontal area for side 2 is L3 times L1, and so that's why the common edge, actually they call it the common edge, is L1 because it appears in the frontal area for side 1 and in the frontal area of side 2. The volume, as I said before, is the multiplication of L1, L2, L3. Another parameter that we see in tube fin and plate fin heat exchanger that we did not see in tube fin compact heat exchanger is beta. Beta actually is defined as the heat transfer area between the plates divided by the volume between the plates. So if I say, for example, for side 1 beta 1 equals the heat transfer area between the plates for side 1 divided by the volume between the plates for also side 1. And the same thing actually for beta 2 is going to be the heat transfer area between the plates and the volume between the plates. This is very important parameter that we are going to use in calculation of plate fin compact heat exchangers. And it is actually listed in the geometry for these surfaces. A is, as you said, the plate, as we said before, is the plate thickness. B1 is the plate spacing for side 1, and B2 is the plate spacing for side 2. Again, this slide shows some types of fins from A to F. A is plain triangular fin. B is rectangular and wavy, number C, or in C figure. Part D shows off-strip fin. Part E shows multi-louvered, and perforated fin is shown in part F. Again, same thing. We are showing the types of fins with different pictures in order to capture or understand the types of fins used in plate fin heat exchangers. I'm going to show you some of the surface data for some of the fins. This is a rectangular fin. The designated number is 11.1. As we see before in gas information for the tube fin compact heat exchangers, the same idea here. You have two parameters in the y-axis, the friction coefficient and the J factor, with two lines. This is representing the friction coefficient, and this one representing the J factor. In the x-axis, of course, we have the Reynolds number. Make sure to understand that it is multiplied by 10 to the power minus 3. So each one of these is going to be, for example, 3 is going to be 3000 because you multiply by 3 about 1000. Here an additional information, geometrical data about this particular surface. But all you need actually in order to do the calculation, you need this figure, and you need these data also. As we said, this is surface 11.1, which is a rectangular fin. Triangular fin, this is another surface from Kazan, London. The surface designation is 11.94 T. This is a sketch for the surface itself. This is the two curves for FC and JH with Reynolds number. The plate spacing, the hydraulic diameter, and so other, the beta, for example, are all listed under the figure. Omega also, the heat transfer, the fin area divided by the heat transfer area also is also listed in the figure. This is surface 9.4 T. For a louvered fin, which is 3/8-11.1 louvered fin. This is another surface, another type of fin. Geometrical data also are here. And just to show you some types of these surfaces. Strip fin. This is this surface is 1/8-15.61 strip fin. Again, the two curves for the friction coefficient and Colburn modulus, along with Reynolds number in the x-axis. data are given, geometrical data are given. So for this surface, actually the data for this surface, how the friction coefficient and the J factor changes with the Reynolds number is in this figure. So whenever you use this figure, this surface, for example, and you would like to calculate the pressure drop or the heat transfer coefficient, you use this figure. In the book, a figure which summarizes some of the surfaces is given. This actually, we have here 5 surfaces, give you FC value, and also the same 5 surfaces gives you the JH factor along with Reynolds number in the x-axis, and then a drawing showing the geometry for each one of these surfaces are given also at the left hand side of this figure. This is just to compare the friction factor or friction coefficient for different values of different surfaces, and the same thing you can also compare JH for several surfaces, how they change with Reynolds number. This is a summary of some of the data in the book of Case and London that I'm going just to present shortly in order just to understand that for the purpose of sizing or rating compact heat exchanger, you need to go to these data and understand it now and utilize it. The main chapter in Case and London that has the information for the surfaces are chapter 9 and chapter 10. The author has divided the chapter 9, for example, into main idea about the types of fins, in addition to other geometrics like, for example, normal flow over a tube of fangs and so forth. But we are going to focus on, for example, in table 9.3, it gives you the geometrical parameters for different fins, starting with A, which is a plane fin, and it gives you the surface designation and in the first column, and then the spacing for that particular surface, the hydraulic diameter, which is written here as 4RH, the fin thickness, the flow length of uninterpreted fin, beta, which was defined before as the heat transfer area between the plates divided by the volume between the plates, and omega. Omega is the fin area divided by the heat transfer area. So with one look, actually, you can look at this and you can see all the surfaces, that is plane fins, and you see all the geometries for all of them in one page. If you move to louvered fin, which is part B here, you see also the same thing, beta, omega, and so other parameters that you can also look at all the surfaces that are available in Case and London that has geometrical parameters in addition to the variation of the friction coefficient with Reynolds number and J factor. All these tables are from Case and London. This is part C, which is for strip fin. We have several surfaces here. Then we go to other types of fins, like part D, which is wavy, part E, which is bin fin, and then perforated fins. We have one surface that you have all the information for that surface. Additionally, you have also this is table 9.4. You have for circular tube, circular fin, you have several surfaces. You should, if you would like to see the any of these parameters, you look in this table and you can find also whatever you need for the calculation of that particular surface. Of course, for each one of these surfaces, you will find the figure that we talked about, which is the figure that shows the Reynolds number variation of Fc and J factor with the Reynolds number for each one of these surfaces. This is part B of table 9.4. This is circular tube with continuous fin. We have only two surfaces. And for flat tubes, continuous fins, we have 1, 2, 3, 4, 5 surfaces. The geometrical parameters are all in here in part C of table 9.4. In order to calculate in order to do some calculations for rating or sizing flat fin compact heat exchangers, you need to know the heat transfer area for both side 1 and side 2. We are going to assume that the number of plates for side 1 is NP and for side 2 is NP plus 1. So, for example, if you have a heat exchanger, compact gas-to-gas compact heat exchanger, we are going to assume NP is the number of plates for one side and the other side is NP plus 1. Actually, it's going to later we are going to assume that they have the same number. The difference is very small between the two, and we are going to assume that the plate spacing for side 1 is B1 and for side 2 is B2. So, for example, if I draw now a very simple geometry like this one, showing just a very rough idea about these two parameters, the number of plates and the spacing, and assuming that this side is receiving gas number 1 and this side is receiving gas number 2, and if we assume that the plate spacing between the plates is given by example B1 for this side. Let me do something different so that it will show what the idea. This is small here, and then we are going to be a big one and small and a big one. So this side for this I'm going to write here 1, and here is going to be 1. So the flow is going to go through these that has 1 in them, and the other side, since the plate spacing is different, so here the plate spacing is B2. So number of if you take this from here to here, this is a common edge, because this is a common edge for this gas and for this gas also. So the number of plates for gas number 1 is NP, and for gas 2 is NP plus 1. Generally, we are going to assume NP. So, for example, if you talk about 20 and the other one is 21 or 19, so NP is the same actually is NP plus 1. We are going to assume that is almost the same. The difference is negligible, as we are going to see later. So if you have a common edge, then actually you can write the common edge in terms of the spacing B1 and B2, in addition to how many plates you have and thickness for each one of the plates. A is the thickness of each plate. So now you can write the common edge as the number of plates multiplied by B1 for side 1, and then the number of plates plus 1 multiplied by the spacing for side 2, B2, plus you have NP plus 1. You have 2 if you add this one to this one, you get 2 NP plus 1, which are the number of plates total, multiplied by A, which is the thickness of each plate. So the whole thing is going to be LC. Now you can take NP from this equation and write it in terms of other parameters. If I say, we can write NP equals LC minus B2 minus 2A divided by the summation of B1, B2 and 2A. So now if you would like to get the number of plates, for example, once you know these three parameters or four parameters, this one, the plate spacing for side 1, the plate spacing for gas 2, the thickness of the plate and the common edge, then you can get the number of plates that you have for that particular heat exchanger. The volume between the plates, if you take one plate, for example, if you take this area here, this one, suppose I'm talking about this one now, and I would like to get the volume between the plates, so it's going to be L1 times L2 multiplied by NB times B1. If I assume this is L1 and this is L2, so if you multiply L1 by L2 multiply by NB, which is the number of plates that you have, L1 times L2 you give you this area, but you have to multiply it by the number of plates that you have, and you have to multiply it by B1. So you get the volume in cubic meters for the volume between the plates for side 1. You do the same thing for side 2, you get the volume between the plates between the two. So what I'm trying to say is that you could calculate NP with known geometry of the heat exchanger along with the common side. You can calculate also the volume between the plates if you know the dimensions of the heat exchangers. You can also calculate the volume between the plates for each side of the thing. Of course, the beta value is the heat transfer between the plates divided by the volume between the plates. So if you know beta, you can also calculate the heat transfer area. If you calculate VB1, if the volume between the plates is known, and beta is known from the geometry, from Case and London books and so other sources, since this one beta is known and VB1, the volume between the plates, is known also for side 1, then you can calculate the area for side 1. Do the same thing also for side 2, so you can get the heat transfer area for side 1 and side 2. In conclusion, if you know the heat exchanger dimensions L1, L2, L3, you know what is the value of the common edge. From the common edge plus B1, B2, A, you can get the number of plates. If you know the number of plates, you can calculate the volume between the plates for each side. Since beta is known for side 1 and side 2, you can calculate from beta and the volume between the plates for each one of them. You can calculate the heat transfer area for each